Okay, hey, we're back. Calc 1, product rule and chain rule, part 2. I only got about an hour to go over some of this stuff, so we're going to knock out what we can, get some of the basics down of the chain rule, and then next time we'll finish up some of the chain rule and work into the quotient rule. But I had a lot of coffee this morning. I'm ready to go. I'm waiting for debate 12:30, so I got time to kill. So we are going to just dive right into this. Link to get in is in the live chat. Anybody can come in, and if you just want to hang out there and watch, that's fine too. So let's go over this stuff. Let me present, and we'll get this going. Da, da, da. Okay, can you see my screen? Let me blow this up a little bit. Zoom in.
Yes, yeah, zoom in a little bit.
Okay. So the other day we went over the product rule, right? So we went chuck all the way down here. We learned all this stuff here. Explained to you how we got the derived the product rule from the first principles, right? So now we're going to be talking about what's called the chain rule. Now the chain rule, unlike the product rule here is when you have the derivative of the product of two functions, right? The chain rule is when you have the derivative of the composite between two functions. Okay, remember the hangout the other day I did the other day, midnight, where we explained composite functions?
Yes.
Right? The reason we went over that is because if you don't know what a composite function, you're not going to really get what the chain rule's kind of doing, right? So that's one of the reasons why we went over the chain rule first.
Well, I mean, I know you only have it. I know you only have an hour, but composite function is basically you put a function in another function, like f.
Correct.
Yeah. So
correct. You're taking the output of one function, you're sticking to another. This is going to be how you take the derivative of one function with a composite of another. So what the chain rule is basically saying is I have f composite g, or f of g. Well, I have the derivative of the function times the composite of the g times the derivative of g. And don't really think about that. That is actually the more formal definition. Think about the way I have it right here. This is actually how it shows in like Wikipedia. You can use different variables, but the concept is the same. This right here, do you see this blue? Let me blow this up even bigger here. This is the best way to learn, I think, using Leibniz notation, how to really learn the chain rule.
Well, I mean, I've seen this, in a textbook I have, and the way they showed that always confused me. So I prefer the other way, using f of x. It's easier for me. Maybe as time goes on, I'll learn.
There's two different ways of doing it with the notations, right? But the conceptually, and let me show you why this one is better. I've done it a couple different ways, but what this is saying is that if you take the differential or the derivative, which is d over dx, so you have dy over dx is going to be equal to dy over du multiplied. This is implicit multiplication, du over dx. These are basically just saying that I have the derivative of y equals the derivative of y with respect to u with the derivative of u respect to x. Okay, and you'll see kind of how this works out as we go along. But we're going to use the first notation first, okay? Just because using that that type of notation, you'll conceptualize what's going on with the functions, right? Using the prime notation, correct? So what we have is, we have two functions. We have f of x equals x squared and g of x 2 of x. We want to have a composite. Remember, the composite was if I have f of g, or excuse me, f composite g, I'm just taking 2x, I'm sticking in x squared. What would be the composite of this function if I have f g of x?
Okay, if you have f of x, g of x, it will be 2x. It will be 2x squared.
Right. You're just sticking this for x, so you just have 2x squared.
Hold on.
Exactly.
It would be parentheses 2x parentheses squared, which would actually make it 4x squared.
You're just taking 2x. You're sticking it in x here, so I have 2x squared. That's it. Boom. You're done. That's all you need to do. Just you can leave it like that. Just 2x parentheses.
Right.
Squared.
Yeah. Right. Never mind.
Yeah. If you want to do it the other way, and you want to say 4x squared, and that's fine. You're right. I mean, you're not wrong, but basically you just stick it in here, then you want to factor it out. That's fine, or make it go further. So it'll be 4x squared, correct?
Yes.
Okay. So let's actually break this down using this notation up here. So what we have is we have f composite g prime, which is your first derivative, right? So this is your definition of the chain rule. So we're just going to stick stuff in here, okay? Since the different notation is this right here. See the f compared to the f of x? This is a long way of writing this, okay? An f is a shorthand notation to writing the function f of x. We've learned that, correct? Yes. So all I've done here is I've just expanded this out to where you have the x involved, okay? That's all I've done is add the argument. Nothing different. Yeah. I just think it explains it easier because now you're looking at it going, okay, I really know this is a function. So here on this side, nothing's changed. But in this side, if you notice what we did was we took the derivative, right, of x, right, which is
of f.
What's the derivative of x squared, which we already know?
2x.
2x. We already get that memorized. Composite g of x. And here, the derivative of x, here, what's the derivative of 2x?
Just x. I mean, 2, sorry.
2. Right. Exactly. So we end up with 2x squared times, wait, 2x squared, how do I get this? 2, oh yeah, I'm sorry. So here we have 2 times the composite function of g of x, right? And the composite is 2 of x. So you take 2 of x, you stick it in here, what do you get?
4 of x squared?
No, it's just 2x squared. It's just 2 times 2x, which is...
Oh, right, yeah, 2 times 2x.
Which is 2x squared.
Yeah.
And then you times it by 2. And you get 4x squared, which is exactly what you said at the beginning, right?
Yeah.
So
well, no, I was just gonna say that in one of my textbooks they actually use to talk about the chain rule. They use 3 gears connected. You know what I mean? Like one gear leads to another. I have to take a screenshot.
That's exactly it. One thing's gonna lead to another composites, right?
Yeah.
And I know we're going over this really fast because I'm probably going over too fast because we're on a time constraint here.
Well, yeah, I know.
I'll probably do another hangout and kind of review this a little bit more.
Yeah.
But I want to give you an overview of what the chain rule does before we kind of jump into it and go to more details of it.
Yeah.
But for something like this, and this is straight from Wikipedia, but Wikipedia doesn't explain it.
Who cares about Wikipedia? I mean, it has a reputation. While you can look at the sources. Never mind. Sorry. Go ahead.
Yeah, it doesn't explain things very well. So what I want to do is I go to the Wikipedia and say, let me see if I can explain this better than Wikipedia does because it's crap. So let's say you have a function like this. X equals e sine x squared. Okay, that looks pretty intimidating.
Yeah, it does. I was just going to say that too. It looks like
it's no joke. But we've already learned how to break things down, right? When we have the composite functions, we learned how to simplify these things. So
yeah, it's like 3 functions in one.
If I want to start simplifying this, the first thing I want to do is I want to take this exponent and make it into a single variable, right?
Yes.
So I'm going to call that, what do I usually call that?
U.
So my y is equal to e raised to the u, where u stands for sine x squared. We good?
Yes.
My u is going to be the derivative. Excuse me, not derivative. I haven't got that far. My u is going to be a composite function of sine of whatever. So I'm taking this x squared, okay? This x squared, well, not really composite, but taking this x squared, and I'm taking that into a variable. So now my u becomes sine x squared, but I'm changing x squared to, we'll call it v.
Yes.
So sine v. So u is now equal to sine x squared, right? And v is equal to...
Oh, x squared.
X squared.
I mean, x squared.
Right. Now, v is equal to x squared. So now we got 3 different things we know. We got y equals to this, u is equal to this, and v is equal to this. Right? We've decomposed it. It's called functional decomposition. We've decomposed it into these 3 variables. You agree with us so far?
Yes.
Okay. Now we can take the derivative of each one of these. Okay, look what happens when we take the derivative of each one of these. Do you remember my hangout when I had the derivative of e to the x?
E to the x is just e to the x.
So what do you think e to the u is?
E to the u.
E to the u. So this one's already done. This one's simple as can be, right?
Yep.
Right, you can't get much simpler than that, right? Derivative of e to the x is e to the x, and e to the u, same thing. So we also went over the other day the derivative of sine, right? Now again, you'll have to eventually prove this to be true, but because we haven't gotten that far yet, I just said, look at this derivative of sine is cosine. Just accept it as true. So what's the derivative of sine v?
Cosine v.
Cosine v.
And the derivative of cosine v is negative cosine, negative
The
sine v.
derivative, well, the
Yeah,
derivative of
going a little
cosine is
ahead.
negative sine, but we haven't got that far.
Yeah.
So here we go. So we've already got two of the derivatives down, correct?
Yes.
The derivative of v, which is same as hx, right? Because we're working with three functions: f of u, g of v, h of x. What's the derivative of v now?
2x.
2x. So I have three derivatives I've gotten now. I just broke this down. I decomposed this down so I can actually take the derivatives.
Yeah. So I'm curious to see how we can handle three functions.
Well, we'll get to that. We'll get to that. This is three functions.
Yeah, that's what I mean.
There's multiple different ways of doing things. Like for the product rule, like you asked the other day, there's ways of doing three products too. They're called triple product rules, but we're not at that point. So we're going to apply the chain rule now. Okay, this little fancy, smancy looking thing, right? What this is just saying again is that we're taking it dy dx, and you might see this written different ways. Matter of fact, let me actually show you how you might actually see this. You might actually see it written like this.
Where? Oh, you're still typing.
Yeah, I'm still typing. So you might see it written like this. Okay, this right here. Can you see this?
Yeah.
This is what you're actually doing. You're taking d dx y, and but see what happens is this goes at this in the numerator. That's all you're really doing.
Oh yeah,
right?
yeah. It's basically times dy is just basically d over dx times y.
Right.
Yeah. It's,
right. Okay. So dy dx, which you're going to see it in this form often, especially when you get into differential equations. This will be the form because you're working with two variables, right? You're working with you start up here. You're working with x and you're working with y. So you're probably going to end up with a differential, which is going to be dy dx.
Yeah.
So now, what is dy with respect to u? Well, it's e to the u, right?
Yep.
Basically, you're just taking these three derivatives, right? And you just times them together. This one represents this one. This one represents this one, and this one represents this one. In other words, dy with respect to u of e to the u is e to the u. So
when you have three or more, you just times the derivative together. You
just
don't
times
have
the derivative together. Yeah. Mm-hmm.
Oh.
Yeah, and so look what happens.
So if you have two, you do f of x composite g times g of x. But when you have three or more, you just times the derivative together.
Well, the two derivatives, you're right. You're going to be just like this one right here. You're just going to be using this formula here. Okay, right? This is your simple chain rule. dy dx is dy du with respect to u, du, and du dx. And again, this could be written multiple different ways. Let me show you something real quick. If I want to write that, I can actually write it, get rid of that, and I could put it as... Right, I can write it like that, implicit. I don't even need any brackets, and I can write this one like this. By the way, I'm getting pretty decent at manipulating this freaking program.
That's good.
Right, and then I can take the du here, copy that, and I can actually make it... Yeah, let's say that worked. Yeah, there you go. Saying the same thing. Okay, it's just, again, this is again dy dx equals dy over du over dx, right? Because these are actually in the numerator.
Yeah.
All right, so let's move on here. And again, I am going to be doing this another over again because we don't have many people watching, but I think it's good to even practice more than one time because chain rule is like the most important rule of all time in calculus.
Yeah, I agree with that.
Right,
that
so
definitely seems... Okay.
So let's continue on. We've already established this right here. We already know that EU is equal to EU. So now that I have this figured out, I can stick U in again, right? And what was U? What did we have to figure out?
Sine x squared.
Sine x squared, correct. So now I can just stick sine x squared, right, in for U right here.
Yes.
And cosine V equals cosine
of V, which is x squared.
Oh, so yeah, x squared. Yeah, I'm sorry, right here. Where is x squared? Here we go. X squared Right now, that's not it. Where the hell is that? Oh, right here. V is right here. X squared. Right?
Yep.
So you always have to go back and reference stuff, right?
Yeah.
That's why it helps
It
to
makes
do.
sense.
This is what I said, when you break everything down step by step, you need to go back and say, okay, well, what is my V? My V is equal to X squared. What do I know? So when you're substituting back in, when it says cosine V, you're actually sticking in what you know, X squared. So I'll end up with E sine
E
X squared times cosine
times
X squared, so you're
cosine.
sticking it in there, times 2 of X, which is just 2 of X, right? So my whole
Yes.
equation, when you move it around, will equal this. And let me add some new lines here so I can put that more to the center. New line.
Steve,
Okay, that should make it.
imagine taking the chain rule of that. I mean, you
You know what?
is
We
there?
can try and figure it out.
Yeah, well, hold on.
But
You know,
let me show
Steve,
you.
is there a limit to the chain rule? How many times you can use it?
No,
Well, I mean, if
because
something equals, go ahead.
actually, excuse me. On this one, if you notice, you're actually dealing with the chain rule and product rule, because you're taking this times this, right? And we know by the product rule is this times this is going to be what we use the product rule for. So you'd have to use both, but this is actually what I figured out on Wolfram Alfram. If you want to see this real quick, okay. So this is what Wolfram Alfram says when you put in that equation. The input is e to the sine x squared, right? 2x e sine x squared times cosine x squared, right?
Yeah, it's a weird plot at the bottom, like weird graph.
It's a weird graph, but look what we got. Do they match up?
Yeah.
Perfectly, right? So that is how you validate if you're getting the chain rule right. That's how you validate if you get it right. Use Wolfram Alpha, stick in the original equation, and see if it comes up with you came up with, right? Now, if you wanted to find out, can we take this one even further, right? Can we go and apply the chain rule again? Well, let's find out. Let's write it out. So dy dx equals 2x. I'm gonna use brackets here because Wolfram Alpha really likes to have things written in a specific way. So cosine x squared. Okay, let's see what it comes up with here.
Would you mind presenting immutable?
Oh, sorry. Okay, there you go.
Oh no, I'm not presenting. I mean broadcasting.
Oh shoot! Yeah, what am I doing?
I meant broadcasting.
Yeah. 1 sec.
That was a slip of the tongue. Yeah.
Okay.
Thank you.
All right. So let me minimize this so I can see what I'm doing here. Okay.
Generally, the fun one, the one everybody loves.
All right. So let's see what this came up with. This actually came up with. This is the equation, but this is what it comes out to be. And it starts getting into imaginary numbers. So it's a very complex Actually, the differential equation solution is pretty easy.
Yeah.
But yeah, when you start getting into the more advanced stuff, you're going to get some pretty wacky stuff. But
yeah. Well, I mean, I was just wondering.
We're going to go with concepts right now.
Yeah, there's a limit to the chain. How many times you can use a chain rule. You know what I mean? Because there's a limit to differentiation where once you reach 0, that's it. You can't really find.
That's fine, but that's not a limit to the chain rule. Again, these are composite functions, right? But yeah, once you reach 0, the derivative is always going to be 0, right? Derivative 0, 0. The derivative of any constant 0, and 0 is a constant.
Maybe it's not a typo, but where it has ddx of e to the u. For the chain rule, wouldn't that technically be e to the u times du dx?
Where, right here? Where are you referring to?
Where it says, remember, ddx of e to the x is e to the x?
That's correct, right? The derivative of e to the x is e to the x, yes.
Right, but where it says below, ddx of e to the u,
yeah, you're right. That should be du, obviously.
Yeah, e to the u times.
I'll fix it. There you go. Yeah, good catch though. See, this is great. In fact, whenever you do like presentations and you're tutoring or you're teaching or whatever, people do make mistakes. Teachers do it all the time. Trust me. But see,
Yeah.
when you understand concepts, you go, well, shit, that doesn't make much sense. You're able to point those things out, right? Because I am taking the derivative with respect to u in this particular case to get e to the u, right?
Yeah.
Right.
If
Otherwise,
it was d to the d to the x, it actually the only way to keep that would be d over dx times eu. That would be your term, the whole thing. So you definitely have to take it with respect to u. Now, we can go on a little bit with the chain
Steve,
rule.
sorry to interrupt you again, but
You're
you
still
know
good
what?
at it.
Can I just have mods so I can present people when they come in without asking
Yeah.
you?
One sec.
Well, you already presented him, so that's besides the point. But yeah, thank you.
Okay, everybody's got mods. Okay, so let me go back here. Now, let me see if I can open up this real quick because I was having. Let me just go to this one. Okay, but we're gonna touch on, and the reason I want to go straight into the quotient rule is because in order to start using the chain rule, the quotient rule is a very good way to use the chain rule to prove that the quotient rule works. Now, you mentioned the quotient rule the other day, and I said, you know, we're going to do that afterwards. So I'm actually going to do that now because of the three, the quotient rule is important, but you can actually use the chain rule to get to the quotient rule. Okay. But once you get to the quotient rule, you don't have to use the chain rule for it anymore, obviously, right? It's proven. So this is a real quick and dirty. This is all this is. And this is straight out of Wikipedia again. But again, Wikipedia doesn't really explain anything, right? Wikipedia just shows you this is this, and they expect you to kind of understand it. But if you don't, you've never been exposed to it, you're not going to understand. So let me explain what Wiki is actually saying here. This is called the quotient rule. The quotient rule is a special type of product rule, basically, except that you know how division is a reciprocal of multiplication, right?
Yes.
Those reciprocal functions. Okay. So the quotient rule is what happens if you have g of x over h of x or f of x over g of x. You have a quotient, you have a ratio, right? So we know that okay, so let's see, f prime, is that right? Or is it should be f g? Let me see, quotient rule. Let me see, I get this right.
It should be f divided by g prime.
Yeah, it should be f divided. Yeah. Where did I get this from? I'm just curious. I got this right out of Wikipedia. F to G. No. Oh, I see. I know what I did wrong. Yeah, I'm looking at it. That doesn't make much sense.
Steve, can you prove the quotient rule using first principles? Or is that too complicated?
Yeah, that's kind of what I'm doing now. But you mean using limits? I suppose.
Well, the f of x plus delta plus h minus f of x over h.
Yeah, you'd have to do the product rule first, I think. But we'll see. I haven't really thought about that to do the quotient rule that way. But let's see what we got. Let's see what we got with this way. Okay. So what this is saying is f of x, right? The derivative is going to be equal to the derivative of one function times g minus f times the product of the derivative of g over g squared. Okay. Or this way of annotating it, right? Because it doesn't really matter what you have for the functions or how you annotate them. It's the concepts. F prime of g is the same as g prime of x times the product of h of x. Okay, so these are saying the exact same thing. I don't think anybody has any conceptual problems with that so far, right? These are just two ways of writing pretty much the product rule. But the g squared, people say, where does that come from, right? Why do you have to divide it by the g squared or hx squared? Well, this is the reasoning behind it. If f of x is equal to the ratio of g of x over h of x, again, these are two functions that are a ratio. Also, you can write a g of x times h of x to the negative 1, because as we learned, hx to the negative 1 is equal to what? If I take something to the negative 1, what does that mean?
It means 1 over h of x.
It means 1 over h of x, right? So it's in the denominator here. So this is just another way of writing this way, so I don't have to use a vernaculum or horizontal bar. I can write it just as a linear form. It's not a linear equation, but it's a linear form, and I can write it with using negative exponents. That's another way of doing it. But if you write it this way, right, what happens is that you can rearrange it a little bit easier or at least I think so. But I want to rearrange this in terms of g of x. Okay. So what I would do is I could rearrange it this way or either way. But if I times, what happens midnight if I times this right here where I got my arrow? Oops. If I times this by h of x and I times this side by h of x, what happens?
In the live chat, he said he's eating.
Oh, he's eating. Okay. So what's going to end up happening is this is going to actually cancel with this one. Okay. If I times it by h of x, and I'm going to be left with h of x on this side. So basically, I'm going to be left with g of x equals f of x times h of x. I'm just basically trying to move this term over here. And the best way to move this term over to here is do the reciprocal function, which is multiplication, because this is division. So if I multiply this side by h of x, this cancels out with this, and I get hx over here. So I'm left with gx equals f of x, h of x. Again, which a PD doesn't explain this to you. But so far, so good, right? That's just basic algebra. Would you agree?
Yeah, so far so
Sounds
good.
good. Awesome. So
go back up for a moment.
Yeah.
Where it says f of x prime. Technically, remember you're doing the quotient between two functions, so it should be f of x divided by g of x, and then prime.
Well, no, that's fine too. It's still f prime of x is equal to. Let's see here.
Okay, I just didn't see that.
Yeah, no, this is actually fine because this is actually how it was written out. Yeah. Because because the derivative of that, right? So let's see here. Quotient rule.
Right.
Yeah, f prime of x. Yeah, that's right. Okay.
Right, but so in the first part, then, where you're representing it as, f prime times g, it shouldn't be that way because that's not what the function is, the quotient between, right?
I agree with you. That's a different way to do it, but that's exactly how it's written here, and that's why I'm using it this way.
Okay.
That's the only reason, because it's just saying f of x is equal to g of x over h of x, and so it wants the f of x here prime because you're going to be substituting this in, and I'm going to show you why they do it that way in a second because I've already worked through this.
Yeah, I think where they're using f, you're using, or where they're using h, you're using f, because they have it as h prime of x times g of x.
Let's see here. Okay, let's compare here. This is what I have. G prime of x, h of x, gx, h squared. Yeah, this right here is exactly this, and that has to be equal to this. This is just another way of writing it.
Right. I don't mean on that side. I mean on the left side, on the left-hand side.
This is the left-hand side. F of x is. Oh, I see. I got you. Yeah, this prime. There you go. That better?
Right, where it's saying f prime, it should be f prime h minus fh prime, right? Maybe, I'm not sure.
Okay, well, let's just work with this because this is really what we're talking about. This is just another way of writing the functions. But I'm gonna actually, you know what? We're just for easier purposes, we're just gonna do this. Dun dun dun, and then go equals. How about that? That's straight out of Wiki. Cool.
Works for me.
All right, awesome. Let's move ahead. So using the product rule on this, we've already learned the product rule, right? Is he still eating? He is, right? Yeah,
I think so. Yeah.
All right. Well, we'll work with you, Mito. I know you know Calc. So if I use the product rule on this, we already know that the product rule has to be the derivative of this function is equal to the derivative of this function with the product of this plus this times the derivative of this, right? Simple product rule. We did a few of them. So this is by using the product rule. I'm saying, okay, I want the derivative of this, and I know it has to be equal to this, the derivative times the product of the function plus the function times the derivative of the other function. So we've got in this step so far. So the very next step would be rearranging. So I isolate g prime of x on one side. Excuse me, f prime of x on one side. I want this f prime of x over here. And the easiest way to do that, which again Wikipedia doesn't explain, but is to actually bring out an h. Let's see here. How they do it? I'm trying to remember. I just did this in my head earlier. F prime.
One way you can do it, right, is where it's where it says f of x times h prime of x.
Yep.
You can multiply that. You can multiply the top and bottom, the numerator and the denominator, by f prime of x, right? So that way the
h of x. Let's see here, g of x. I actually just did this in my head this a few minutes ago for f. So I'm going to subtract. Okay, so here we go. Watch this. This is again. I had to do this in my head. So g prime of x. If I subtract this right here and I move it over here, right? I move this over to this side. I get g prime of x minus this, which is actually it'd be this one. I'm sorry. So this one is moved over here, right? G prime of x minus f of x h prime of x. This would be the top row, right?
Right.
And then I divide each side by h of x. There you go. Pretty simple. I'm just taking this right here, right? And I'm moving it to the other side. And when I do that, I got to change the sign, right? So g prime x minus this gives me the top right here, correct? And then you have this left, and what happens is when you divide each side by h of x, this goes away, and I'm left with this minus this over h of x. You agree?
Yep.
Okay, so this will isolate f prime of x. Now, since f prime of x is g of x over h of x, which we've established up here, right? Then we can say that g prime of x minus g of x over h of x times hx prime. This is just, again, saying, let's see here, how to get here? I'm trying to remember g of x. Oh, yeah, because I'm just back substituting it in. Because this right here, we're just substituting f of x, right, with this. That's all we're doing. Okay, so it actually works out to this. So when you actually get your whole formula, I'm just basically taking this and I'm sticking it in for f of x. Oh, not right there, right there. Okay, so when we get that, then we have to figure out how to factor this, right, to get to the equation we want. Well, one of the ways to do that is times by 1, right? And anything that equals 1, h of x over h of x is equal to 1. So I can actually multiply the top by h of x, right? And it makes it multiply the bottom of h of x. If I multiply the top of h of x, I end up with g prime x times h of x, which is right here. I end up with g prime x over h of x times h of x, which cancels that out. And I end up with h prime x over h of x, which will give me h of the x squared on the bottom, because it's hx times hx. And if you want me to actually break that out, I can do that. Want me to separate them out so it makes more sense?
Steve, doesn't the division line with the above the multiple by needs to be longer? This the division line is like the g prime and the h prime needs to be also divided by h.
Yeah, I can do it that way. 1 second. I can fix that. I see what you're saying. My goodness. This, I don't know how they got that way. Should have actually. I forgot a bracket, I guess. Oh, that didn't fix it. Let's see here. Bracket. G of x. That's a bracket, and get rid of that one. I'm losing a bracket here. G of x is 1.
I think it's easier to just delete them and then write them beside the g.
All right, let's just rewrite it, because I see exactly what you're saying, and you're right. So let's just try to rewrite this the correct way it should be doing it.
Yeah.
All right. So
first g prime x.
Well, f prime x. We're going to do it the whole thing. F prime x. This is actually good, because this actually shows we kind of try to have an understanding of what's going on. Okay, so g prime of x. You know what? Let's just do it this way. I got a better idea, so I don't have to rewrite the whole thing. Yeah, I just typed this over twice. Okay, see that? And then what we're going to do is we're going to substitute this right here into here and see what we can get. See if it works on the program. This is more of a program thing than it is conceptual. It's just kind of writing it to where it actually works out. So let's see if we can get g of x over. Let me copy that and paste it in the other one. So please work. Please work. One sec. Come on. Now it's frozen. Ah, come on.
Sometimes when using software like this, it's easier to perform the division operator first so that the line is automatically fit.
Yeah, but it's not letting me change anything now. All right, hang
Yeah,
on,
maybe refresh.
yeah, let me reopen it. This is the quotient rule, right? Okay. This is why I wanted to switch. Another reason why I wanted to switch to the Linux is because it uses a different thing, LibOffice, and I like it better. It doesn't have this Office recovery stuff that I keep having to do, and doesn't freeze as much.
Have you tried it with like Microsoft Word or anything like that?
I would tried it with what?
With like Microsoft Word?
No, I don't have to use Microsoft Word, but it's very similar. And Microsoft Calc and Microsoft Writer and all that. All right, so let's see if we can do it. Let me should be back where we were, except for this right here. Okay. Okay, so I've got this doubled here. So let me see if I can just copy and paste this in here if I get it to work out right. Okay, I know it's supposed to be, and I'm just trying to do it in the program where it can actually make sense. Here we go. Did it do it? No. Okay, look at this. Look at it. H over. This is what I want to copy, and I want to stick this into for f of x. There we go. We're getting closer. We're getting closer. And then bear with me, guys. It's gonna be a long day. Is that right?
Why did you just write ER?
Yeah, it's not gonna work. You know what? Let me just. How about we just forget that, and I'll just show you how it's supposed to look. Because I have to figure out how to actually.
I think I have made it myself on Word. Let me show it in a moment. I think it should be. It should look like this.
No, that's not it.
But I could be wrong. I could be wrong.
One sec. One sec. Let me see what you got. But I know it. I know how it's supposed to look in my head, but I can't make it to work out in the program. So let's just look here. We're going to go to quotient rule on Wikipedia, and then I'll look at your thing. Okay, so this is how it's supposed to look.
Yes,
right?
I think I got it exactly right.
Do we know Charles? I think.
Yeah.
There we go.
Let's see what you got. Yeah. That's exactly what it says here. See?
Ah, I see. So that's
so what I had was right. I didn't have the denominator.
So that's how you would do it.
Let's look at this very carefully, though, before we go any further. Again, this is a programmed problem. This is not a conceptual. This is just getting the program to look like this, right? And it requires a little bit of finesse. But let's look at this, and let me blow this up so you can see it better. Same thing you had there, Ness. Okay, you can see that pretty well.
It's very small. So what you are showing on.
Yeah. Okay. One sec. Let me try something else.
I can just see it, but I think the live chat would get very trouble with it. Seeing.
Yeah, there we go.
Yeah.
Oh, too much.
It's too much. Now it's good. Now it's great. Now scroll up, I think, a bit, and there we go. Yes.
All right. So this is where we're at. So let's actually look at this. Okay. So all we did was we just back substituted gx of h of x for f of x here, which is what I was trying to do, but the program wasn't allowing me to do it. So, or at least I have to figure out how to do that. I'll have to work on that. But basically, all we're doing is we're back substituting this into this. Now, the easiest way to get rid of this hx in the bottom here, right, is to times the top and the bottom by h of x. Okay, when we do that, the h of x here is going to go away, right? But I'm going to end up with g prime of x times h of x, which is right here, right? And I'm going to end up with h prime of x times h of x. Let's see, that's going to go away here. And then on the denominator, I have h of x times h of x, which is going to be h of x squared. So basically, I wish I could show you in the program. Just imagine right here, you're just timesing this by h of x on the top, divided by h of x on the bottom. Okay, similar basis.
And because the h x on the top, that will cancel out the h x right there.
This right here, this is where you're going to visualize it in your head. The g of x times h prime of x is all in the numerator here. Okay, it just doesn't show it, but this right here, this h of x, right, is actually up here in the numerator. So when I times that by h of x, right, it cancels out with the bottom one in the denominator, leaving me g of x times h prime of x, leaving me this term here. Now, do you guys see how they did it to get the h of x squared on the bottom? You just times the top by h of x, you times the bottom of h of x. Well, when I times the top by h of x, I end up with g prime x times h of x. The other h of x gets rid of this h of x on the bottom, leaving me gx times h prime of x, which is this. And then h of x times h of x is hx squared. That is,
I can see it, yes.
Okay, that is how the quotient root is derived, right?
Maybe can you do it step by step to show it what happens?
Yeah, I'm gonna try.
It's difficult. It's difficult to show.
Yeah, you know, well, I'm probably gonna do this again. I'm probably gonna do this particular one twice because I think it's critical. But let me see if I can actually just type it out here. Get rid of this.
Rearrangement, but the rearrangement is obvious if you don't see steps.
Yeah. So I actually kind of put it in here, but I didn't show the actual steps. So let me see if I can say h over x. So we take. Oh, by the way, this is all hosted up here. I'm just going to get rid of that because that's completely wrong. This is why I wanted to use the other program. So much easier than this one. Get rid of all that. Okay. So I want to take this formula here and I want to times it by this, right? Would you agree? So that's this formula here. So that's my, and what you can see I'm doing is this is how you have to type it in. You have to type it in a command line. This is what makes it so difficult. So I want to take this particular formula, and we're just going to make some space down here. We're going to take that, and we're going to multiply. We're going to give that a new line. We're going to say times h x over h x. There we go. And then I just put brackets around this, and that should fix that up. Okay, let's see, bracket that. Bracket that. And put an end bracket. God dang it. You see, am I missing brackets somewhere? That one has a bracket. That one. Oh, I see the initial bracket. Oh, that's not right. Come on, guys, help me out here with these brackets. Okay, that's my initial formula. Right? That's my initial. And I want hx squared. Oh, this is not going too well. Why did I not copy the whole thing? If I get rid of that, and I isolate that, that'll give me that times quantity h squared over. I don't want to show brackets. H x over h. I can't even type. Okay, but I want this to all be on top. There we go. There we go. Getting closer, getting closer. But this is actually. I almost got it. Almost got it. There we go. God. See what a pain this is, right, guys? See? It's not that simple to do this kind of stuff in this program. Okay. So can you see what's going on now? Okay. So, God, this is not the right formula, is it? I want to multiply this one.
Okay, well, hold on. Why is there?
Yeah,
Never mind. Never mind.
This is wrong here. This needs to be that. Oh, about time. Let me add a little spacer in here. So now we may not be able to see this. Okay.
Honestly, I don't know. I don't know how you have patience using this program. I probably would have just
I'm
stopped
not
using
kidding. It takes a lot of effort. There's a lot of little symbols in here, like spacing symbols and stuff. Okay, so this is what this. Now we're back on track. And again, we'll be doing this presentation over again because this really sucked. But chain rule is not easy, guys. And this is just scratching the surface. So what we're doing to get the wicked proof, and the wicked proof is correct, yeah. But the way they did it was they took this formula here. Let me get rid of this. Right, and they times it by this. Well, the denominator is easy, right? Hx times hx, you know, is hx squared. Nobody's going to have a problem with that, right?
Nope.
Okay. The top, what happens is, that's still not the right formula. God damn it.
Right, that's why where it says f of x times h prime of x, it still needs to be divided by h of x, so that one of the h of x's cancels.
I'm going to do it this way. Screw this. We're going to do it this way. We're just going to show you on this one. We're just going to go back to wiki proof. Look at when you times that by h over h, hx by over hx, what happens? The bottom goes to xx squared. We already agreed. The top, the hx will be times by this, giving you this, right, Midnight?
Yep.
Okay. The other hx, since this right here is actually in the numerator, when I times this whole thing by h of x, all it does is get rid of this bottom one, leaving me g of x times x prime x, which is this. There you go. That is how you go from this to this.
That's how you approve the product rule. Quotient rule, sorry.
Quotient rule. That's how you prove the quotient rule, what's called implicit differentiation, which we haven't really got much into yet, explaining the difference between differentiation and, implicit versus explicit. And I'll get into that eventually. The real simple, though, the way to kind of think about it is that if I have an explicit function, I'm expressing it in terms of like y.
Well, I mean
that I have y equals something. That is explicitly giving you what the formula is, right?
Yeah, implicit.
What's the
well, I was just going to give an example of implicit. Implicit. I think it's function. Well, anyway, an implicit would be x squared plus y squared equals 25. Let's say the equation of a circle.
Right. And then what do you do to the 25? What do you try? What form do you want it in? It's actually r. The form is in the form of r
squared.
Well, no, it's r. I'm taking it as point notation. RPQ, I think, equals 0 is point notation. Somebody really advanced math would probably remember. But basically, you're right. But you want to get that 25 to 0. Basically, it would be.
Well, yeah, but Steve, that's
x squared plus y squared minus 25 equals 0. You want it in that form. That would be your general form for the implicit. And by the way, circle's not a function. Yeah, circle's a relation.
Yeah, relation. My bad.
But the reason why you want to do implicit differentiation over explicit sometimes the equations are very, very complicated to work with explicitly. And I'm going to do a whole presentation on that alone because it is something you must understand in calculus. So you're just not going to get calculus. But let me just show you something real quick, what I mean by that. But and this is all really off the top of my head because I don't really.
Well, I mean, Steve, if you're talking about implicit differentiation, why don't you do? Why don't you do like 2x plus 2y times the derivative of y minus 25, or actually no, it was 0. Then you do the minus 2x, on both sides, and then you would divide. So then you would divide by 2y, and you're left with negative x over y.
One sec. Nobody's going to be able to do that in their head right now. One sec.
Well, no, but
Okay, so can you see this? You can see this equation here.
yes.
Mhm.
Okay, to express that in terms of y explicitly, why I have y equals something is ungodly. If you want to see what it actually looks like, because I can't. Wolfram and Alfred won't even do it. I have tried this before, and I remember Wolfram Alfred said, "Fuck you." It won't even try. It just doesn't do anything. It just gives you this weird root shit. I believe it will for n equals what should be for y3 minus y, but for y5 it's just a screw you. So let's check this out and see what we got from Wolfram Alfred. And I'll show you why it's a lot easier to do an implicit differentiation.
Isn't it just y equals 0?
Okay,
Yeah.
so this is and then we want to solve for y. Now if we want to isolate y, it basically no, see, it didn't do it. I want to get y by itself, but I don't remember how I entered it before. It was a long time ago to actually get that to be in terms of y. Let me try yq. Let's see here.
Well, yeah, because I mean, why would I guess y would equal 0 because because if you factor out a y,
Oh, minus x. Wait, one sec. Oh, here we go. That's what it is. Okay, I had the wrong formula. That's why.
oh, that's
This should be actually because you're working with two variables here. Come on, guys, keep my toes. This is nearly impossible to write explicitly. Okay. Again, I haven't looked at this in a while, so coming a little slack. But if I just have y cubed, look at the solution. Okay, it's ridiculous, right? To express it explicitly in terms of y, right? Who the hell wants to bother with that, right? So
somebody who really likes math. I don't know.
I couldn't know. Yeah, I wouldn't even know how to even begin to write that explicitly in terms of y. I mean, except this is what Wolfram Alpha comes up with. But let's take it simple and just do it. Let's make that a 3 there. So let me go back in 3. Yep.
Oh,
I got it. Okay, so if I want to express this explicitly, it's going to be very, very difficult. But if I want to do it implicitly, then all I need to do is take it derivative as is written, okay? And if you actually look here, let's see here. I lost my Wolfram. Where did my Wolfram go? There we go. So let's actually take the derivative using Wolfram and see what it does. I want dy dx and see what it comes up. Okay, so it found that pretty easy. 1 over 3y squared minus x. Okay, and if you actually look at this, you almost be able to do it in your head. It's basically, what's the derivative of y cubed? What's the derivative of y cubed?
3y squared.
3y squared. What's the derivative of y?
1.
1. So you end up with 3y squared minus 1 equals x, right? And then
yeah,
all you do is you just move this to the other side of the equation, because you have what dy of dx with respect to x is equal to 1, right? So I end up with 3y squared minus 1 equals 1. I move this to the side of the equation. I get my y prime equals x 3y squared minus 1. So it's a lot easier to do an implicit differentiation than having to go through and trying to express it explicitly in terms of y. And again, I'm gonna have a whole presentation on this. This is just completely off the top of my head right here. So if I had to actually do this, I think it'd look like this. I haven't done this shit in years, man. Walk me through this, because you guys probably have had this way shorter than I have. And then I get dy over dx x. Okay, does that look right so far?
yes.
Okay. This is pretty good. I'm just kind of going with this. So, line. Okay. So we're gonna have a 3y squared, right? We know that one's pretty easy. Yep. God damn it. 3y squared. We know that dy dx with dy with respect to x for y is going to go to 1. No, wait. It's going to be equal to 1, and then this is going to be equal to. Is that right? No, wait.
Hold on. Y, y 1 times y derivative of y.
Well, remember that it's correct, except for it's being done with respect to x, so it has to be multiplied by dy dx.
Yeah, but that's that. Okay, so actually, let me do it how I think I remember how to do this. Over dx with respect to y. Let me just do this in my head as I'm walking through this, because this is completely off the top of my head. That one you can't do anything with, so let's just leave it like that. And then dy dx is, with respect to x is going to 1. Okay, so let me make a new line. So I end up with dy dx over dxy equals 1 divided by 3. 3 over 3y squared. And then, no, see, that's not working right.
Right.
Man, it's been a while since I've done this.
dy dx of y.
Where did I mess up?
1.
Where did I mess up?
dy dx of y is still 1.
Is it still 1? It makes sense. I thought so, but I wasn't sure. So you should end up with dy dx 1. Okay, you should end up with this, right? Is that right?
Well, not quite, because the 3y squared on the
I still need a dy dx in there somewhere.
Right. On the left-hand side, where it says 3y squared minus 1.
Yeah, that one should be.
Was done to the wrong variable. You still have to include dy dx.
So.
Yeah. What you could do is just put the 3y squared minus 1 into brackets, and then times dy dx, and then just divide, and then you will get 1 over 3y squared.
Oh, wait. No. All right, help me out here. It's been a long time since I've done implicit differentiation like this. What am I missing here? Because I know what it's supposed to be. I'm just trying to remember how to get that.
Well, the trick is that when you're doing when you're taking the differential of y with respect to x, you have to multiply by dy dx because it's not being done to the correct variable. So when you take the derivative of y cubed minus y, you apply the power rule, but you multiply it by dy dx to denote that this is being done to y instead of with respect to x.
Okay, so this is dy dx. I'll fix this in a second. So, wait. That. And then this is wrong here. So this is actually 1. And this is actually a minus. Oh, and almost there. Nope, that's not right. 2y squared minus dy dx. Let's see, this should all. I really hate this program. This is supposed to be an isolated term. This needs to be. There we go. Is that how it's supposed to look?
Exactly. And with the minus 1, it also has to have a dy dx term as well.
Also has a dy. Okay. So let's see. You know what's funny is I kind of got it in my head, but trying to get this damn program to do it, that's what sucks. Okay, and so this is because this is being with respect to x. That's why. But this y dx of x is with respect to x. So this is actually equal to 1. So this one is 3y squared, but it's still a dy because it's respect to x, right? And same thing over here.
And you know
exactly.
I actually told you before. I mean, I know where you're going. So you would just factor out the dy dx, but
yeah, you factor out the dy over dx. So let's do that right now. Dy over dx.
Before before I said it would be 3, like braces. No, not braces. Parentheses 3y squared minus 1 parentheses times dy dx, and then you just divide. Like, you know, I
got you.
missed.
Yeah, no, we all know how to do this kind of intuitively anymore. We're getting this program work. There we go. I'm getting closer here. Get rid of that.
That's what I was saying.
There we go. Okay, so we factored out the dy dx with this quantity, right? Right.
Remember
that. This is actually kind of good review, man, because I'm going to be doing a presentation on this, so I'm going to have to know this shit. So now we can just divide each side by. Oh, I forgot a y in there, by the way, guys. There you go. So now I can just say dy dx over dx equals 1 over 3 quantity 3y squared minus 1, and dy dx is the same thing as saying y of x, so I end up with y prime equals dun, dun, dun. And there we go.
Oh, I don't get scroll up a bit. I don't get how you get from.
That's the answer.
Oh, yeah, but there's a step
Well,
that I don't get.
I'm sorry. Where did you? What step?
Okay, see, from the top formula to the second formula. That step I do not get.
Okay, right here.
Yes, that's from the one below it. Yes.
This one.
Yeah, to that one. Yes.
All we did was factor out a dy dx. Look at, if I take dy dx and I move it out here, I'm left with 3y squared. If I take dy and dx, I factor it out, I'm left with minus 1. Think about this. What happens if I just distribute this as multiplication across addition, or subtraction? Remember, we already went over distribution of multiplication over
yes.
subtraction.
Now I see. Yes.
Now if I just take this and I distribute, I got 3y squared dy dx minus 1 dy dx, which is this.
Yeah, it's just simplified. For example, if you have a times 2 minus b times 2, you can just write it like two how do you say it in English? Those signs. I don't remember.
But you see how we factor this out?
Yes.
So we got okay.
I can type it down in the group chat to see what I'm saying.
It's the same thing as if you were saying 2a minus 2b and just simplifying it to say 2 times a minus b.
So, but real quick, the problem was 3y cubed minus y equals x. And we put in a Wolfram Alpha, it got this answer, and we were able to see this was cool because we were able to actually figure out what we needed to do to get the right answer in the right steps, right? So I'm actually okay with this. I haven't done implicit differentiation in 25 years, so that's the first implicit differentiation problem I've done in decades.
And Steve, can you see what I wrote in the group chat?
Yeah, they say thumbs down. Well, whatever.
Yeah.
I'm gonna be doing this one over again anyways. This was a dry run.
Well,
but anyways, we gotta get ready for the debate here, so I gotta get links out and get it set up. So we are
okay. 3:30, right? 12:30 your time. 3:30.
Yeah.
On your channel. Who's King Cockduck debating again?
Wayne Fillmore.
I have no idea who that is. Hopefully, it should be entertaining.
We'll see.
What's the topic?
All right, guys. So we'll see you guys in about 30 minutes on my channel. I'm gonna get the links out, and then we'll do this same thing over again, and then I'll get the math program down where we can actually kind of go over it better. It seems like everybody got the concepts. We all understand the math. That's the problem. That's not the problem. The problem is that getting the software to show it, yeah, tricky. Yep. All right, guys. So see you guys in a half hour.
Yep. Bye.
Bye.